Our mic isn't working yet, so don't give it to us when it's going to be back.
All right. So welcome to the Portable Data Lake workshop. My name is Adrian. I'm a co-founder of DLT. And today we will learn about what the Portable Data Lake is and what the technologies out there that enable us to do this are and what's the state of them. So can we use them? So why are you here? I know that most of you are here because of Iceberg. There is some hype around Iceberg right now. People feel like it's ready. So they want to know about how to use it. Some of you want to save compute cost by using Open Compute. You want to be autonomous and use open source tools. You want to enable cross-tech collaboration like across clouds or across teams, or you want to add compliance to a data lake. So what will you learn in the next hour? We will have an intro about the state of technology. In the open compute, we'll look at the open standards that enable this compute portability, and we'll define the portable data lake. Then we will have a hands-on workshop with Hiba and Anun. And then we were supposed to have a short demo, but we don't have the recording yet. Didn't make it to us. So what we will do is just present a few more slides. So let's look at the current state of Open Compute. So the current state of Open Compute, you could say, is starting from division. So in the last decade, the data field split into two areas. One is operational business user support through SQL and data warehouses, and the other is machine learning. So people running complex algorithms against large batches of data. And those two areas used largely the same data. It's the business data, but they did so in different ways, resulting in different end requirements and different technology stacks. So Camp SQL required flat typed data in SQL databases, so they were able to serve business users through tools like, doing pivot tables on SQL tables. And Camp Data Lake wanted just, big blobs of data so they could explore them. So there is convergence towards the lakehouse because ultimately these two fields use kind of the same technology, so they could work on the same tech stack if they agree. So because of the different requirements, we have things like Delta Lake that appeared 5 years ago. We have Iceberg, it's 6 years old, and we have even Apache Hudi, which is even older than that, 8 years old. So these are table formats that enable separating compute from the table storage. So how do we choose between these different table formats? Everyone's talking about Iceberg. We already use Delta quite widely. And if we look at the features, they all kind of look the same. It's a little confusing. It's hard to tell what's going on. So they have all very permissive OSS licenses. They have different maturity in different areas. Things are constantly changing a little bit. We hear things about the catalogs. We hear things about the catalog wars. So how do we take decisions about what to use? So when we compare these table formats, we could start with Spark support, and we can say, yeah, all of them have excellent Spark support. That was kind of like the idea out of the box. When we look at Python support, we have different pictures. So for Apache Iceberg, we have PyIceberg. It's still developing. It has limited features. It's heavily reliant on external catalogs, so it's not quite production ready. For Hudi, we have Hudi RS. It offers standalone Python support with all the necessary stuff, reducing dependency on Spark or external catalogs, and it's quite production ready. And then we have Delta Lake with Delta RS, which is actually quite mature, production ready way to use table formats without Spark or catalogs. So when it comes to vendor logs, we have for Apache Iceberg, we have the catalog dependency kind of built into the whole concept, because for Iceberg, the metadata is stored in catalog. So this makes the whole usage of the files dependent on that. And when we look at the Iceberg part of it, at the library, even it is behind right now, so it might be some time until it reaches parity with Spark. But even when it gets there, it will still have this catalog dependency. For Apache Hudi, things are operational. You can just use it. And for Delta Lake, again, because we have metadata stored next to the data, you don't actually need to use a catalog. But if you do, you need to be careful of vendor locks. When we compare for Python first users, Iceberg aims at maturity to remain dependent on catalogs. Hudi is open to use in Python, and basically Delta Lake is ready to use. Sorry if I'm a bit repetitive. Key takeaways for Iceberg: use it if you care about schema evolution, about vendor neutrality, consistency across many engines, or large petabyte scale data. Don't use it if you want mature Python support, or if you're doing streaming or frequent updates, or if you want a catalog-free setup. For Hudi, use it if you're doing streaming or high-frequency data changes like updates on your data, and if you want vendor neutrality. But don't use it if you want advanced schema management, or if you want mature Python support, or large-scale or complex, if you have large-scale or complex data modeling or data processing. For Delta tables, use it for its great asset transactions, time travel ability. It's great with Spark for streaming or batch, and it has a mature Python support. And don't use it if you want a vendor neutral stack. It has a bit less multi-engine support than Iceberg and less advanced schema and partition management than Iceberg. And then there's always DuckDB. We haven't been talking about it, but this is kind of like the minimum unit of a data lake. We could go with DuckDB for local cases, but it's certainly not very scalable. It's not suitable for massive data sets. It does lack essential features like asset transactions in case we care about those. And it's inadequate for multi-tenant environments, but it's pretty good for development. So let's move on to what is a portable data lake. Well, a portable data lake is quite hard to explain, but essentially it does for a data platform team what DLT does for a data engineer. It's a collection of utilities that leverage open source standards to enable to develop in better, cleaner, governed, and more efficient ways. So it features a data cache that enables local development. It can be fast synced to online. It's pip installable. You create packages that are pip installable, pipelines that can be modified or reused as a dependency. So you could imagine it kind of like Docker, where you can use base images. You have governed data sets, enabling simple data mesh without adding technical parts. And you have a local catalog that is enabling separating metadata from serving and development with the data. So why is this important? Well, it solves actually a lot of problems around data access and development with data. Just as Docker changed the face of development, Portable Data Lake aims to do it for data teams. So you could say you have 10x developer outcomes and a focus on value add and not technical patches, which is the stuff that matters. So onwards, my colleagues, Anun and Hiba, will present the collection of technologies that we can use to create a portable data lake. And after they're done, I will show you a few slides of how we approach the problem. So Anun, would you like to take over?
It says you're in the stream.
Okay, how about now? How about now? Is it okay now? I'm assuming yes. Okay, then I'm gonna share my screen. Can everybody see my screen? Can you see the screen? Because I seem to be sharing my screen, but I'm not sure if it is. Okay, yes. Then let's start. To understand the concept of a portable data lake a little better, let's take a look at how the POC version would look like with DLT and Ibis. So let's start with DLT, the data load tool. My assumption is that many of you already know what it is and how it works, but to freshen up a little in this section, I'm just going to cover the definition along with a simple example and a more extended example, as well as cover the file and table formats DLT supports. And in the end, elaborate a little on why things we cover in this collab matter for today's topic. So
Just close this so that the screen is bigger.
okay, how about now? Okay, so what's DLT? It's an open source Python library that you can install with pip. What it does is that it extracts data from different custom sources, normalizes what needs to be normalized, and then loads everything to the destination. It handles schema evolution, has a data contracts feature, supports incremental loading, and allows you to manage the performance of your data pipelines. For each one of these topics, check out the respective doc pages. There are also recordings of our previous workshops on how DLT works, so feel free to check them out and learn what DLT is and how it works in more detail. So another thing that needs to be mentioned is that DLT has verified sources and destination combinations, meaning there are pre-built pipeline templates that you can install with this command here, DLT init. I'm personally a big fan of those because they cover most use cases and are easily adjustable if you know some Python. So to get the feel, if you don't already have it, how DLT works, let's run a simple DLT pipeline where we load a Python dict to DuckDB. First, we obviously install DLT, then define our DLT resource, which will yield the dicts, then create a pipeline, and eventually run it. We see that the pipeline ran successfully, and we can check what has actually been loaded into the destination. And yes, Kai Santos was loaded 10 times in the destination. Note that you can control the normalization if you have specific requirements, but here we can notice that the name field, which is a nested dict here, was normalized into two fields, name first and name last. So now let's take a look at an extended example, which involves the GitHub API and the file system destination. We'll be using the local file system, to be specific, a folder named data lake. And as usual, we install the dependencies, define our DLT resource that fetches GitHub issues from our repo with pagination. We then wrap the resource in a DLT source, which is a logical grouping of resources. Essentially, DLT sources correspond to datasets and the destination, while DLT resources correspond to tables. Okay, sources to datasets and resources to tables. We then create a pipeline here where we decoratively define the destination as file system and run the pipeline with Parquet defined as the loader file format. In the end, we can see that yes, indeed, everything was loaded into the local file system in a folder called Data Lake within a dataset called GitHub Raw, the name of which we defined here. And yep, the table folders include Parquet files. So everything was done correctly. Now that we've seen that DLT can create Parquet files from the data in the file system destination, I think it's good to mention now that DLT also supports JSON-L and CSV, and how you would define them in the pipeline is that you would simply pass the correct string in the pipeline run as the loader file format argument. And if you're only getting familiar with different file formats, we included this image here so you understand the basic differences between them. But the bottom line is that the ability to define these different file formats in your pipeline in an easy and decorative way is what matters. But most importantly, the very option itself to use different file formats is what's the most important in terms of the portable data lake concept, because it provides adaptability. Now, since we're talking about data lakes, we can't not cover table formats. Adrian already did, but I also included a simple definition here so that maybe there are people who do not know and might, for whom the specific sentence might be useful. So DLT currently supports Delta for the file system destination. How you would define it is as simple as, just like for the file formats, you would pass the correct string to an argument, but in this case, instead of the pipeline run, you define it in the dlt.resource decorator as a table format argument. And then we simply rerun the pipeline with write disposition replace because we don't want to be appending data. And yes, everything that was loaded successfully. And if we check the local file system, we would see that indeed the Delta table format was used because the corresponding snappy file was created and the Delta log folder. So DLT also supports Iceberg for the Athena destination, and how you would use the Iceberg table format is that, again, we first install the dependencies for the Athena, and here we included the image of how you would define credentials for the Athena destination because it's in the cloud. Since it's a little bit tricky to use the .dlt folder in a Colab environment, we're just using environment variables, which is the equivalent of the whole thing here. So we define credentials, then we redefine the DLT resource. Note that this is exactly the same get issues resource we used earlier, and we just changed the table format from Delta to Iceberg. And then we create a separate pipeline for the Athena destination and run it with the loader file format Parquet. Note that the Parquet is used as the default loader file format, but for the sake of clarity, we're defining here explicitly. So in the end, what you will have in your S3 is two datasets. In this case, two datasets only if you set the same bucket for the staging and the Athena destination. Here we use the same bucket URL, and we see that both the staging and the dataset that's being used by Athena are created in the same S3 bucket. And if we go to GitHub Raw and then check the individual table folders, we will see that the Iceberg table format is in use indeed, because there are the two corresponding folders, data and metadata. So why table formats matter should be a little bit obvious right now, but yes, they provide data management features that ensure consistency and efficient access for multi-platform use. And we also have a roadmap for Iceberg, so stay tuned. The next tool that is relevant for the portable data lake is Ibis. It's also easily installable with pip install, and it's essentially a unified Pythonic API for different backends, which you can use to interact with your data. So let's first cover a simple example. Ibis uses DuckDB as a default backend. We are going to be using Ibis to read the Parquet files we loaded earlier into our local file system using the default DuckDB backend. So what it would do is, as usual, install dependencies, import Ibis, and then simply read the Parquet file this way. And note that DuckDB in this case only reads the metadata, so there's no full load of the entire dataset. And then you could do the usual operations like filtering and grouping here, and it works like a charm. What Ibis does is that it practically bridges the disparity between the data science experience and data engineering experience, because the first prefer data frame operations and the latter are more used to SQL. And it provides a unified experience for both sides. And as an extended example, we're going to be showing how to use Ibis with different backends other than DuckDB, and how you would do it with the Polars example is that you create a connection. Okay. You would create a connection and use the exact same method you used for DuckDB. And the result is the same. And in the end, we can check if the Polars backend was used. And yes, it was indeed used. For BigQuery, it's exactly the same, other than the fact that you have to define credentials because it's a cloud tool. So we define the credentials here, create the connection with the credentials, and run exactly the same code. And the result is the same. And in the end, we can check that BigQuery was indeed used. And yes, it was used. So why it matters is that Ibis provides a unified querying experience across diverse backends, and combined the file formats, table formats, and the unified querying tool is what makes data lakes more flexible and portable. So basically, they allow you not to be in the clouds all the time. That's what it's about.
I think you're gonna have to invite me, but also keep
Okay.
my own.
So that, yeah.
I'm there, right? Okay. Maybe I should turn on my mic.
Okay.
What about now?
There's 2D. Oh, that's a 2D. It says she's done it. Okay, perfect.
So I speak.
Yes, it should work.
I am speaking. Okay. Right. So Anoon introduced to us some tools, and now we are going to put them together in some workflows to try and. We're good, right?
I think so.
Yeah. Okay. Yeah, to see how we can put it into a local development and an online development workflow. So let's start with that. First of all, why do we need a local development workflow or local environment? And the easiest answer to that question is that we need to be able to test something before we put it into production. We love tools like DuckDB, like Daxter, because they give you a place for local development and testing, and you don't essentially have to put out fires as you're in production. Because also in most places, you can't really put things into production straight away. There are barriers, there are tests and checks. And you can't just put anything into a production environment, and you have to test it. Perhaps you are testing your pipelines to put it into some sort of an orchestrator. And for example, you're using Airflow, which is not the easiest to start with, whether you're setting it up locally or whether you are doing it through Docker. It's not the easiest experience, it's not the best experience. So, those are some things that me and I'm sure a lot of people like about Daxter, about DuckDB, and even dbt in the way that, it can locally serve you documentation for your data and your data models. So, yeah, that is a basic introduction to why we need local development workflows, which I'm sure you know of. So here we have a task. We have a task which is we want to find the number of open issues for each user in GitHub. Since you're already familiar with the pipeline that Anoon introduced, we were using the GitHub issue source. And let's walk through a little bit of the workflow, right? So first of all, we have a source. We put it into a local file system destination through DLT. And now we are going to use Ibis's DuckDB connector. And then we're going to put it into our testing destination. Since we're focusing on testing, for this demo, we will be using a local file system, but of course, your testing environment can be online as well, which we'll get to just after this example. So yeah, our Ibis is going to float on our DuckDB connector, and that's how we will use it to model our data. So first of all, we go back into defining a resource, just like we did. We have to then read from that resource from a particular Parquet file, which this will obviously be different for everyone. But what's stored in our data is this one. So we'll read it using Ibis, and then also using Ibis, we'll do the transformation on it, which is basically taking all of the open issues, filtering it by open issues, and then grouping it by every user, and then basically getting all the count for users who have open issues. So yeah, that so far we have designed the resource. Now we have to put up the pipeline and then run it to basically store it into the file system, and we just do that with pipeline run. And we see that it has been loaded into your local file system, and there are no failed jobs, so we're good to go. And that was like a very, very short example of how you can use DLT and Ibis to read your data, to load your data, to take your data from one place to another very easily and in a few lines of code. So then we move on to a little bit more of online workflows and online development. And when we say online, we can either think production, or we can just think of any online destination where we want to work with. In the previous example, we were focusing on the words testing, and testing, again, does not exactly have to be local. It can also be online. But yeah, so there are a lot of things that you can think of when you think about development online. And when you do that, you can think about sharing your work. You can handle bigger data sets, and you can do everything that the cloud allows you to do. So we will take the exact same thing that we were doing in the previous section, and then we will put it into an online destination, and it will now look a little bit like this. So we take our same source, we take the same source that we were working with, we use DLT to put it into an online destination, which for this demo we have chosen as Google Cloud Storage in a bucket. And then we'll use Ibis's BigQuery connector, which you see it's floating on Ibis. And then we use DLT to put it back into your storage or online destination. So to do that, first, as Anun went over the credentials for Athena, you're going to have to do it for GCP buckets as well, which you have to set up a configuration or secrets.toml file. You start with installing DLT with Google support, and you can do this part as a secrets.toml file, but in Colab, it's just easier to manage these secrets as environment variables. So we'll be doing that. Yeah, and we have a bucket called Portable Data Lake and the rest of the credentials that we put in. And now we have the exact same code that we ran for dumping your GitHub issues into your local file system. We'll just use the exact same code, also write destination. But since you've now set up credentials, DLT will know that your file system is indeed online. So you can run this and you can load all of your data. And when you look at your destination, you should have your data set right there, which we also called GitHub Raw. So it exists there, and your issues table exists there with a certain bucket file that we will be using for transformation. Now, the second part is also very similar to the one that we had above, but now since we are reading from Google and not just our local file system, then we will need to set up credentials and basically just give it the path to your bucket file that you want to be transforming. Here we have chosen we have cherry-picked one particular file, but if you're in production, if you're applying this to a multitude of files, you can also do that. Which I think you're just gonna have to put a asterisk at the end of this. And yeah, you can pass this to your BigQuery connector, which will read your data, and then also we apply the exact same transformation, the filter of open issues. We get all the users which are grouped, and we just take this data and put it back into your file system online destination, which gets loaded successfully. And you can see that GitHub transformed Ibis, which was the name of the dataset that we gave, is now online as well with our resource, which was issues count by user. So yeah, that was an example of using this in a local environment, this entire workflow in a local environment, and also in an online environment, pretty much summed up. Now, before we give the stage back to Adrian, we just want to, do a recap and put this into a big picture. So we can say that there are many ongoing discussions around these topics, like the composable data stack, the modular data stack, open standards, and open compute. And all of these talk about issues like portability or moving your data around, interoperability or glue code, like connectors, which we just saw, but they are vendor dependent. And they also rely on the structure and format of the data and tables in the destinations, the way that they're handled. And all of this aligns quite well with the solution that we have presented today. So yeah, thanks to Ibis and DLT, you can kind of move around this data from almost anywhere, and you can run this entire Colab or anything like it wherever Python runs. So it's pretty easy to use. And all of this enables you to create your portable data lake. And to recap our two workflows, we took our GitHub source and we put it both into a local and online destination. And then we transformed it using Ibis and its different connectors. And then we put it back into our local or online destinations, or testing or production destinations, or however you want to call them. And we did that all in a few lines of code. So that is it for the demo. We would love to hear your input, your questions and comments, and please join our Slack and post them there. And then, yeah, engage with us so we can get back to you. Yeah, and now I invite Adrian back.
Thank you, Hiba. Hey, folks. So a little more about the approach that we're taking towards building our version of the portable data lake. So we say that ours is composable for multidisciplinary data teams and built on open standards. So what exactly is it? So just like DLT is a 10x extract and load pipeline development experience, the portable data lake aims to do the same thing for data platforms. So it's a composable, portable, pip installable data mesh ready data platform. It's built end-to-end. It's for building end-to-end pipeline packages, so kind of like self-contained data packages, pip installable and reusable. And it's meant to be used with your own tool stack. So accessing data through DLT's catalog via SQL or Python, or pip install via your own tools. And I'm going to talk a little bit more about it and present you some phases of it, and move to the Iceberg roadmap. So now let's look at what composable means. So composable means using open standards. It means using Ibis for abstraction, Arrow under the hood for fast sync from local to online. It also means taking advantage of the latest features or benefits of each technology. So for example, Parquet, Iceberg, DuckDB, or various vendor formats. Portable means portable code that can run on various technologies. Portable pipeline package that can be pip installed or depended on. Portable components that we can interchange. So for example, if we can change the compute or the file format. And portable data access and local catalogs. And if you look at this screenshot from the presentation, it's actually of one of our early demos for the portable data lake. And that's basically a catalog in a Colab notebook that is governed. When it comes to governance, data mesh ready for us means semantic data contracts as config. So where previously, if data mesh is an adaptation of microservices, then the semantic data contract is basically a simplification of the governance API. So you have the same information, but in an abstraction that is accessible to the data person without adding complexity. And it has built-in access control, because ultimately, if you have a local catalog, what you would be missing is access control. So this is why we added already there. There's a metadata catalog for various functions, PII governance, and fundamentally the data packages that you build can be pip installed, inspected, modified, or built on. So let's talk about our Iceberg roadmap. Part of the reason why we talk about portability is because it allows us to leverage technologies like Iceberg sometimes sooner. Sometimes it allows us to do something different locally. So let's look at our Iceberg roadmap. What we want to do essentially is full support for the Python ecosystem. So what this means is our goals is we want to achieve full write and schema evolution support on Iceberg, no backends and no servers unless you want them. production-grade Iceberg maintenance functions, so compacting files, vacuum deletes, basically all the stuff that needs to happen in the background when you're working with it in a production environment. And of course, portability of the query engine and the catalog. If you want to use them, you can use them. And we want to reach this goal by investing in OSS by Iceberg and, of course, OSS DLT to enable the creation of Iceberg data lakes from Python. Then we want to build a production-grade portable data lake for Iceberg. So this is a commercial offering. And finally, we want to support some of the existing vendors in the open source, so for DLT. So our timeline in terms of actual time looks like this. Early December, we hope to support partition writes, append and replace on Iceberg with Python. Metadata would be stored with the data in a technical catalog. So it's not meant for user access. It's just meant for technical access. We can actually keep track of the tables. And the DLT client will be extended to enable queries on Iceberg tables from local file system. So in December and January, we want to add support for other catalogs and query engines similar to how we currently support Iceberg on Athena. And in Q1 and Q2, we want to enable production-ready Iceberg lakehouse on the portable data lake, which is fundamentally where you'd be doing your transformation or your compute. Finally, we have, of course, a call to action. You can find the links in the description of this video. So for open source DLT, if you're a fan, sign up to our newsletter for product updates. You can find it on Substack, join our Slack community, and of course, give us a GitHub star. This kind of stuff helps raise awareness to your network, and it helps us grow. And for the portable data lake, if you're interested in the commercial offering, you can sign up to our waiting list, and we'll send you updates as we make progress on the topic. And if you want to be an early design partner, we have a few slots where we can cooperate with some people. We'll give you early access, and you can give us feedback, and you'll be able to influence our direction. So thank you for being with us today. If you have any more questions, please ask them on our Slack channel. And once more, thanks Anun and Hiba for their support with this workshop, and I'll be seeing you around.